Okay. Hello everyone. Today our last day of summer school, and Federico will give last lecture. And I would like to thank you for all you and to join us. And also thank you, Federico. He gave great lecture. You can start.
Thank you for the introduction, and thank you for organizing, you and Mustafa for organizing this summer school. And I think it was very interesting for me to review a lot of the material that I've worked on during my PhD. And thank you to everyone who came. And please feel free to drop me an email if you want to discuss any of the topics that I talked about today. So today, this week. So today I will conclude this lecture, these lectures talking about calibrated submanifolds of the Foscolo-Husky-Nordstrom manifolds. So as I've tried to do every time so far, let me recall you that previously in these lectures we introduced the notion of a G2 manifold, which is a manifold with some special free form, which is closed and co-closed. And they have comass less or equal than 1. So they are calibrations. And the two calibrated submanifolds that we have are the associatives that are calibrated by phi, and the co-associatives that are calibrated by star phi. And these are characterized by the fact that the star phi is vanishing on it in the associative case, and phi vanishes on co-associatives. So you can characterize them using this condition here. And associatives are also characterized by the fact that they preserve this cross product. So today I will discuss the Foscolo-Husky-Nordstrom manifolds. So Foscolo, Mark Haskins, and Johannes, what they proven a few years ago was essentially a classification of all ST2 squared times C1 invariant complete G2 manifolds. And as you could imagine, this is a cohomogeneity 1 technique. So as I also explained previously, so my manifold splits into a principal part, which is the one in green, where the orbit looks like SE2 squared over K naught, and is going to collapse in on one end to a manifold which looks like SE2 squared over K. So this is just to give you, to recall you how these manifolds look like. Okay, so the goal of our lecture today is to construct calibrated submanifolds here. And of course, the only thing that we know about these manifolds is that they have symmetries. So the idea is once again to use the symmetries. So the subgroups that we consider is going to be T2, and it's the T2 sitting inside SU2 squared times C1 in this way here. So we pick a U1 sitting in SU2, the identity over the second copy of SU2 and U1. So we are looking at T2 invariant associatives. This is what we're going to do. And let me just mention that T2 invariant associatives should also play a crucial role in counting associatives, and a lot of fancy technology that I'm not the expert about. But what is important is that, as I mentioned last time, when we have a group action on our manifold, my manifold is going to split into some singular parts and some principal parts. So the orbit space here, M over H, will look like MP over H, so the principal part quotiented by this H action, and some singular sets that are represented by S1, S2, and S3. And our goal is going to be to look for curves in this quotient space, which with pullback of this curve in the ambient manifold MP to be associative. So the problem, of course, is that my manifold is my Bryan and Salomon manifold. Sorry, my first-law Husky Nordstrom manifolds. They are defined by this free form. We have G2 structure defined by this free form here, and A and B are functions that are only defined implicitly. They are solutions of some ODE. So if I want to solve such a problem, I would have to solve an ODE problem with coefficients depending on A and B, which are implicitly defined. This is, of course, a essentially impossible task to do, and so we need to find a way around this problem. What so we will need some help from multi-moment maps that I'm going to discuss very briefly here, and these are beautiful geometrical objects that have that turned out to have many applications in other contexts as well. So I guess most of you are familiar with moment maps in symplectic geometry. So if I give you a symplectic manifold, which we're going to assume to be simply connected for now, then and I pick a subgroup of my symplectomorphism group. So these are the diffeomorphisms preserving my symplectic structure. Then I can observe very easily that if X is one generator of my group action, then since I am preserving omega for any F, these equality holds. So the Lie derivative of omega with respect to my generating vector field is 0. And by Cartan's magic formula, this is telling us that the derivative of Ix of omega is 0. Or in other words, I of X of omega is a closed one form. And so as we assume that my symplectic manifold is simply connected, then it's the derivative of some one function, of a function eta. So more generally, we can then define the moment maps. The moment map is a map from my symplectic manifold into the dual of the Lie algebra G of my Lie group, which is defined by the condition just above. So the derivative of mu paired with my element of so mu X is an element of my Lie algebra. So mu paired with X is going to give me a function from M into R, and the derivative of such a function is the contraction of omega with X. And this makes sense because of his observation here. Okay, so it turned out that in symplectic geometry, multi-moment maps were extremely useful and powerful objects. For instance, they can be used to study Lagrangian submanifolds, symplectic quotient, Kähler quotients, and etc. etc. But the problem is that in our context, in the G2 world or in the spin 7 world, we don't really have a two form. We don't have a natural two form, but we have a natural free form and the natural four form. So we need to find a way to exploit this idea in higher forms. So the setup for my multi-moment maps is the following. So I have a closed geometry, which is just a manifold with a closed form, alpha, which I'm going to assume to be simply connected for simplicity. And I pick a group G, which is in the automorphism group of my manifold, which essentially is the symplectomorphism group, but with respect to my K-form alpha. So it is it's just the same setup for any generic alpha instead of a symplectic form. Now, the idea would be, instead of plugging in one vector, so one generator of my Lie group action, then I want to plug in k minus one of them. And if I plug them in, I need to assume that the derivative of this contraction here needs to be zero. Because if this is the case, then I can define in the exactly same way a function mu from m into the k minus one lambda k minus one g star. So I need to pair my function with a k minus one generators of g, and picking this contraction here, I get a real valued function, and so I can take the derivative, and this needs to be equal to my term above. So this is the idea. Unfortunately, there is a big obstruction for this to work, and the problem is that in general, such condition here cannot be true. A simple example is SU2. So if I pick SU2 and E1, E2, E3, the generators of the Lie algebra, such that the Lie bracket between E1 and E2 is equal to E3, so this is a standard basis of the Lie algebra of SU2, then if I plug in two vectors into my alpha, which is a free form, then I see that by using Cartan's magic formula and the formula on how the Lie derivative commutes with integral product, then you can see quite straightforwardly that what you get is alpha contracted to the third element, E1, the Lie bracket of E1, E2, which a priori is not zero. So all I'm saying with this example is that a priori the pairing, this condition here, is non-trivial. Okay, any question on the definition of on this idea of multi-moment maps? Okay, so okay, now we want to find a better definition. We need to find a condition on my Lie algebra such that I can exploit the circle of ideas here. And so let me recall that a multivector for me is a section of this bundle. So, and the decomposable vector, multivector, is a multivector of the form x1 wedge xk for xi that are elements of that are vector fields. So for multivectors, I have a natural contraction which is induced by the obvious one. So if I take k a decomposable k vector here, and alpha is my R form, then I can just plug in x1 xk into my alpha, and this is a well-defined contraction map. Okay. Now on such a space, I also I don't only have multivectors, I also have this other quite funny space, and there is a projection from my funny space into the multivectors. So the reason why I am talking about these things is because a priori on multivectors, I don't really have a well-defined Lie algebra bracket, because the difference between these two is that for the composable vectors, once I pick my vector fields on the right, then I can't factor out functions out of my gamma, while I can do factor out functions on my multivector space. So for this reason, it makes sense and it's well defined, a natural contraction, Lie derivative, and Lie bracket on such a space. And if Q is my element of this lambda kr of gamma Tm, then I can just define Qi as the contraction by the if term. So I'm just taking out the if term, and Qij is just taking out the ith term first and the j term afterwards. And similarly, I can define a Lie derivative of my multivector, which is defined in this way. And I can also define essentially a Lie bracket by this formula here. So this is nothing crazy. It's just the natural extension of the Lie derivative and the Lie bracket in this context. So the upshot of this part of the talk is just that as for k-forms and one vectors, I have the so-called Cartan's magic formula. I can extend the Cartan's magic formula for k vectors, and the formula that you get is this one here. It doesn't really matter too much, but the point is that Madsen and Swan 10 years ago, they proven that essentially there is an analogous formula for multi-k vectors. And a consequence of this formula is that if you just pick k equal to 1 and pick your element, your k vector field to be a one vector field x, then this formula is just the contraction of Ix d alpha plus the derivative of Ix alpha equal to the Lie derivative of x alpha. So we recover exactly the Cartan's magic formula, the standard one. Okay. In the context of that we will be working on, alpha is going to be closed. So the first term always vanishes. And the third term is also going to always vanish because we are picking elements that are preserved by so G generates G is in the automorphism group of my closed geometry. So the third term is also going to vanish. So all you get is d of the differential of the contraction that I want is 0 if and only if the contraction with this funny Lie bracket map is equal to 0. So essentially, if this map L is trivial or the image of L is 0 for my Lie group, then I can exploit the same idea that I mentioned before to construct these multi-moment maps. So, I mean, this is just a way, this was a formal way to just tell you, look, all we need to check is, so the correct definition I need to define multi-moment maps is this k Lie kernel of G, which is defined as the kernel of the map defined above. It doesn't really matter the formula explicitly, but I felt like it was good to if you're interested in the topic, to go back to the slides and figure out all the details. But so the typical examples are, so if G is abelian, then let's go back to the definition of L. Then if my Lie group is abelian, the left hand side, this term here is always 0, and so I'm in a good shape. So if G is abelian, the k Lie kernel is the whole lambda kg. And obviously, if k is equal to 1, then the k Lie the one Lie kernel is just the Lie algebra of G, and you can check for SU3, for SU2, what are the 3 and the third and the second Lie kernel And for the group that is going to be of interest for us, you can check that these are the correct second and third Lie kernel. So it doesn't really matter massively, but the important thing is that we can now, using such a definition, define multi-moment maps, which are just maps from into this subgroup of lambda k, subalgebra of lambda kg, for which the usual definition of moment maps can be extended naturally. And similarly to symplectic geometry, multi-moment maps were extremely useful and studied, for instance, in for toric G2 manifolds and toric spin-7 manifolds. Are there any questions on multi-moment maps? Okay, so I'll move forward. Okay, now I can talk about G2 manifolds with T2 times SG2 symmetry. So we will want to construct G2 manifolds with certain I want to construct T2 invariant associatives in certain G2 manifolds. And the brightness, the fourth color Haskell notion manifold will have a additional SC2 symmetry that commutes with my T2. If you go back to the previous slides, you could check that. So my argument is going to be general enough, so I can consider any G2 manifold with such a symmetry, and I will now explain how to deal with this case. So I'm given my setup is I have a G2 manifolds with a homogenized 2 action of C2 times SC2, which preserves my T2 structure phi. So this means that I have a T2 times SC2 homomorphism into the automorphism group, and the kernel of these homomorphism is just a discrete subgroup of T2 times SC2. This is just to ensure that we have the principal orbit to be of dimension 5. Now, the first goal of our discussion is to understand the stratification that I discussed. So the stratification induced from the orbit type stratification theorem. So let me recall you that if you have a Lie group acting on your manifold, then your manifold automatically splits into a principal part and a series of singular parts. And now we have a T2 times ST2 action, which preserves some additional structure. And today I will tell you that you can actually characterize all the stratification just from this data. But first, let me stop some notation and some observations. The first notation is I will define by G the action of T2 times ST2 quotiented by the kernel of this homomorphism. So if I quotient by the homomorphism, of course, this action is going to be with a trivial kernel, and so it's an effective action. Now, given such a G, then we can also define two subgroups of gamma, which are just given by the intersection of gamma with the T2 times the identity component, and the gamma 2 is instead the intersection of gamma with the identity part of T2 times ST2. So in particular, from this T2 times ST2 action, we can construct an effective T2 action and an effective ST2 over gamma 2 action. So this gamma 1 is the kernel of the induced homomorphism from T2 times the identity over ST2, and the same for gamma 2 is the kernel of the homomorphism from the identity of C2 times SC2 into the automorphism group. Okay. Now I also I am going to define S to be the singular set of the T2 action. So the reason is we will be interested in particular in such a set because outside of this set, the T2 action is going to be with two-dimensional orbit, and so we have local existence and uniqueness by the local existence and uniqueness theorem of Harvey and Lawson. Finally, from this group, we can also construct two subgroups that are gamma tilde 1 and gamma tilde 2, and these are just defined to make this diagram in the sense that I'm going to explain now. So if we start from my principal part, then I have the action of G on my MP, and this action of G induces a quotient, which is MP over G. There is the orbit space of my principal part. But MP is also endowed with a T2 action and an SC2 over gamma 2 action, which are effective actions. So MP can also be decomposed into an MP over T2. So this is the orbit space of the T2 action. And since SC2 acts on MP, then up to the quotient of this SC2 over gamma tilde 2, then I have a GSC2 action on MP, and so I can quotient by that as well and get MP over G. And in a similar fashion, you can do the same trick doing SC2 first and T2 later. So this is just to say that since my T2 action and my SC2 actions are compatible with each other, they commute with each other, then my quotient splits into two quotients. Okay, any questions on this? Okay, so now I will state the theorem, the main theorem about the stratification of my G2 manifolds with T2 times SC2 symmetry. So I pick a point of my manifold and I define by T the tangent space of my orbit and by N the normal space of my orbit. Now, the theorem that I proven with Ben was that the dimension of a stabilizer cannot be bigger than 4. And the reason is if the stabilizer were of dimension 5, then so then I would have a three-dimensional. So the rank of my group couldn't be 2. So the GX would be five-dimensional. So it would be T2 times SC2. But if it is T2 times SC2, then it has rank 3, but G2 has rank 2, and this is a contradiction. Doesn't matter. Then what you can prove is that if the dimension of the stabilizer is 0, then we need to be just the identity. So the only so what this implies is that the principal stabilizer is trivial and there are no exceptional orbits. Then the second result is that if my stabilizer has dimension 1, then it needs to be isomorphic to S1, and we also would know that X is not in S. So this means that the T2 action at that point is non-trivial. And GX, so it doesn't have kernel, sorry, stabilizer. And the action on the normal bundle, so the slice action, is completely characterized by the fact that it acts trivially on one-dimensional space, and there's rotation on the two-dimensional space. So if the dimension of a stabilizer is then two-dimensional, then its identity component is isomorphic to T2. And in this case, we are a point where the T2 action is, we are a point of the singular set of the T2 action, and the stabilizer of G acts on n diagonally, which just means that T2 is a diagonal subgroup of SU2. And moreover, you can prove that the orbit is an associative submanifold. So the tangent space is associative. Finally, finally the last case is when the stabilizer is three-dimensional, and if the stabilizer is three-dimensional, then it needs to be isomorphic to SU2. We cannot be in S, and the slice action is trivial on a one-dimensional subspace, and as SO4 on a four-dimensional subspace. So, and the last case is dimension equal to 4, and so in this case, the identity component is isomorphic to U2. We are in the singular set of the T2 action, and we know how the action on the slice is just as U2 on SU3. So all it matters really for us is that given a G2 manifold with a T2 times SU2 symmetry, then you can write down and understand very precisely how your manifold looks like near every stratum of your certification. So if you pick your orbit, then you know how your manifold looks like near the orbit. And this is precisely governed by the slice action and the slice theorem. Okay, I will prove the first instance of this theorem now. This is just so that you know what entails. And so the proof goes as follows. So we first claim that if the T2 times SU2 action at a point is discrete, then we need to be in the center of T2 times SU2. And the way to prove it is the following. So we identify the tangent space as the Lie algebra. So this is just obvious because the tangent space of the orbit is just given by, so the subgroup is discrete. So the orbit is 5-dimensional and is generated by the Lie algebra. So in particular, we can split my tangent space of my ambient manifold as the tangent space of the orbit plus the normal space n. And I know that T2 times SU2 x acts as the adjoint representation on the first two factors. Very well. So now the action on T2 needs to be trivial because T2 is abelian, and since we preserve the G2 structure, then we also preserve the cross product of the generators of this T2. So in particular, this means that n splits a line N1 on which my T2 times SU2x, my element here, acts trivially. So on TXM, we have my action, which is trivial on T2, trivial on N1, and N2 is a one-dimensional subspace. So since we preserve the metric, then G acts on N2 as plus or minus the identity, because we preserve the metric. Now, if my action on N2 is also trivial, then the only possibility that we have is that it acts trivially on SU2 as well, and so we're done. because at that point, the joint action on T2 times T2 plus SU2 is trivial, and you can argue that we are abelian. By contradiction, we need to assume that G is equal to -1, so we act on N2 as minus the identity, but then we also need to act on SU2 as minus the identity, and this is a contradiction. Okay, so the second claim that we're going to prove is that the principal stabilizer of G is trivial. And the reason why this is the case is because by first claim, all the principal stabilizer are in the center, and so they're equal to each other. But now, as the action is effective, all what you get is that the principal stabilizer is trivial. From these two claims, we can conclude, because if we take X in M with zero-dimensional stabilizer, then you can prove in a similar fashion that Gx acts on the normal space as the identity, but by the slice theorem and the principal orbit type theorem, we have a neighborhood of my orbit which intersects the principal part. And since we intersect the principal part, there we act freely, and so the stabilizer needs to be just the identity. Okay, this was quite involved, and it was a representation theoretical proof, which I don't know if it was of your taste or not. But let me just say what are the geometrical consequences of the certification that I told you about. So what we know now is that the singular set of my group G splits my manifold into 4 embedded manifolds that are S1, S2, and S3, and S4, which are characterized by the dimension of the stabilizer at the point. And you can compute the dimension of each of these singular sets, and these are 5-dimensional for S1, 3-dimensional for S2 and S3, and 1-dimensional for S4. Moreover, what we also have proven is that the singular set of the T2 action corresponds to the singular set of S2, corresponds to S2 union S4. And this is how we should imagine the values S1, S2, S3, and S4 look next to each other. So this first picture means that if I am near S1, so if I pick a point in S1, then near S1 I either see another point in S1 or MP, unless I am very, very close to S2, and in that case I see 2 copies of S1 and the principal part, and a similar argument worked for S3, S4, and S1. Now, the idea for this is the following. So if we look at S1, we have that the action of a stabilizer on the normal bundle, we know the splits as N1 plus N2, and the action of Gx on N1 is trivial. So if I move along N1, I stay in S1, so the stabilizer doesn't really change. And so the dimension of my S1, which would a priori be 4, now becomes 5, because I can move along this N1 direction. And similarly, if we look at S2, then my action is kind of like the one of T2 on the normal space, and there it's I don't have any fixed set, so I remain 3-dimensional as expected, but I see 2 copies of C where the stabilizer is 1-dimensional, and this will correspond to the 2 copies of S1 here. Okay, let me go on by talking about the second goal of this talk is to understand the multi-moment maps in the G2 manifolds with T2 times SU2 symmetries. So I told you that we need to look at this K-Fleet kernel. And in the case of our interest, if we pick U1, U2, the generators of T2, and V1, V2, V3, the generators of SU2 satisfying these conditions on the Lie algebra, what you see is that the only possible multi-moment maps that you get are θ1, θ2, nu, eta, and mu. And these are precisely these, everyone characterized by these differential. So these are defined up to constants, as in general multi-moment maps are. And the exercise that I give you is to check that these precisely are all the possible multi-moment maps in terms of the K-Fleet kernel. And so the properties of these maps are the following. So nu, you can quite easily check that is T2 times SU2 invariant. So also the gradient of nu is going to be T2 times SU2 invariant. Mu is also going to be T2 invariant and SU2 equivariant. So the gradient of the absolute value of mu is T2 times SU2 invariant. Now, θ1 and θ2 are T2 invariant and only SU2 equivariant. And eta you can check is SU2 invariant. So in particular, the gradient of eta is SU2 invariant. These are just standard properties of my multi-moment maps that you can check by just plugging in the correct generators of the T2 times SU2 action. Okay, any questions on this? Okay, then the last observation that I forgot about, but it's quite crucial, is that the zero set of my multi-moment map here is contained in the singular set of my T2 times SU2 action, but also contains the singular set of the T2 action. So we will see that this is going to be crucial for understanding the topology of my T2 invariant associatives. Okay, we're now ready. We've done our homeworks, and now we can talk about these T2 invariant associatives. So the setup is once again my G2 manifolds with T2 times SU2 symmetry. And we want to describe the T2 times of identity invariant associative in such G2 manifolds. So the idea is that if we work outside of the singular set of the T2 action, which we denoted by S, then a T2 invariant submanifold a priori looks like a donut trail. So you have a trail of donuts here on M minus S, which when you project down to MP over T2, or actually M minus S over T2, what you see is a curve. And conversely, if you start from a curve gamma on the quotient space and you pull back, then you're taking the donut trail above your curve gamma. So this is a three-dimensional subspace. Now we want to understand what is this curve gamma and the associative upstairs. And what you can show, and it's quite easy to do, is that T2 invariant associatives upstairs correspond to integral curves of U1 times U2, where or equivalently the gradient of my multi-moment map nu. And this can be just shown because U1, U2, and U1 times U2 span an associative plane. Now, a consequence of such a theorem is that the problem of finding T2 invariant associatives is splitting with the stratification. And the reason is that the integral curves of U1 times U2, so the gradient of mu is invariant under the T2 times S2 action. So if we move along the integral curve, we won't change the stabilizer. Okay, now, because of these observations that we split together with the stratification, then we first deal with the principal part of the T2 times S2 action. And as I mentioned just now, since MP is contained in M minus S, then my T2 invariant associative will look like a trail of donuts on MP, projecting to a curve gamma, which is the integral curve of U1 times U2. And MP over T2 is a 5-dimensional manifold, and so understanding integral curves of some implicitly defined gradient function is still very complicated. And now we are going to use the fact that we also have an SC2 action. Indeed, now we have an SC2 action, so we can project to the quotient of my GSC2 action. So we project down my curve gamma to a curve on the quotient of my T2 times SC2 action. And since U1 times U2 is T2 times SC2 invariant, we get an integral curve of the same vector field downstairs as well. So this is still difficult, this problem, but what we can do is to find first integrals of our ODE system. And what Ben and I have proven was that mu, so another multi-moment map, is constant along T2 invariant associatives. And so the curve gamma downstairs looks like the level set of my absolute value of mu, so of my function mu. So to sum up, what we have proven is that if I pick a connection on MP over T2, so my quotient space here, viewed as a GST2 bundle over my surface MP over G, and such a connection needs to be taken such that U1 times U2 is in it, and the metric induced on the quotient is such a connection. But in this context, so a curve in MP over T2 is associative, so it's an integral curve of U1 times U2, if and only if its pullback is associative, but also if and only if it is a horizontal lift with respect to this connection of the level set of this function mu. And computing the multi-moment maps is much, much easier than computing integral curves. In this way, we have characterized T2 invariant associatives in the principal part. And by the corollary of the last slide, we can show that complete T2 invariant associatives are topologically diffeomorphic to T2 times R. And the reason is, since we are in the level set of some C, and this C cannot be equal to 0 because we are in the principal part, then we are going to stay away from the singular part at all times. Okay, now I don't think I have much time, so I will push forward to the singular part. So the singular part is divided into the different strata. So in the first stratum, we have S1, and S1 admits a SC2 equivalent submersion from my singular stratum into S2, and S2 is just the unit sphere, two-dimensional sphere. And the fiber of such a submersion is a T2 invariant associative. The way to see this is by considering the kernel, so the generator of the a stabilizer, and this generator of a stabilizer has the terms B here, B1, B2, B3, which is an element of S2, and the map going from S1 into S2 is precisely the maps that we need. Now, for the last two cases, so for S2, you can see that S2 is a G orbit and is associative, and this follows essentially from the representation theory that I mentioned at the beginning of this lecture. And S3 union S4 is a totally geodesic smooth associative, and this again follows from the representation theory. Okay, in the last 3 minutes, I will mention very briefly how we can apply all the theory that I talked about today to the fourth-color Haskins-Nordstrom manifolds. So, as mentioned, it is crucial to understand the stratification first. And the stratification, in order to understand the stratification, we need to understand the group action. And the group action on my manifold looks like this. So we have a T2 acting on, so e to the I lambda 1 acts on the left on the first factor of SP1, and e to the I lambda 2 acts on the right on the first and second factor of SP1, and gamma, which is an element of SC2, acts on the left on the second factor. And from this, you can essentially sit down and understand what are the stabilizers of these groups. And on the principal part of the SC2 times SC2 times C1 action, you can immediately see that the only singular set is S1, which looks like this thing. So it's just the points where P is either complex or so complex, I mean, spanned by real number plus I real number, or P is spanned by J times real number plus I real number. And on the singular part of my SC2 times SC2 times C1 action, then the then we either have an S2, which looks like which is diffeomorphic to S3 and is associative, or we have S3 union S4, where S4 is given by this formula here. And finally, the non-trivial term, the non-trivial part is the one involving kappa Mn. And in this case, we split into an S1 part and an S2 part. So let me give you the conclusion since I ran out of time. So the conclusion is that in the principal part of SC2 times SC2 times U1 action, which is given by this formula here, then we have a principal part and two singular parts with one-dimensional stabilizer. And on the principal part, I have a map from my MP into R4 with T2 invariant complete associatives. And these are of topology T2 times R. On each Si, S1 here, I have a map from S1 plus minus into S2 with totally geodesic T2 invariant associatives, and these extend to the total space of my four-scalar Haskins-Nordstrom manifold, and F and R smooth, and of topology S1 times R2. Finally, on the singular part of my SC2 squared times C1 action, then if kappa is diffeomorphic to SC2 essentially, then this SC2 squared over kappa is a three-dimensional sphere and is a T2 invariant associative, while if kappa is equal to kappa Mn, then I have one singular part with one-dimensional kernel and a singular part with two-dimensional kernel. So for the S1 tilde part, then we have once again a mapping to S2 with further directed to invariant associatives, and S2 is AT2 invariant associative. But in this case, all these associatives are compact and are topological length spaces. So this is the conclusion of the theorem, and this is essentially all I wanted to say. Sorry for going over time, and thank you for your attention. I hope that you enjoyed a bit of calibrated geometry with symmetries, and hope you learned something out of these 4 hours. Thank you.
Thank you so much for your lectures, and I think we had a great week. Thank you again.
Thank you.
And is there any question and comments? I think there is no question or comment. So